Hello everyone. This is our final project for the SC205 Discrete Mathematics course Winter Semester 2022-2023. Our project is based on data compression and this is the web page of our project. As you can see, these are our group members and these are our professors. Going down, we see these are our project details, which include PPT, code, LaTeX file, YouTube video, and application link. Now jumping straight to the PPT section, we encounter our PPT. Well, it's easier to access it from the PowerPoint presentation, so I'll just do that. Again, these are our group members. So, why to compress data? Why did there arise a need to compress data? Well, in this rapidly evolving world of today, we desire everything to be as efficient as possible. In this technological world, we innovate more and more to comfort ourselves with efficient solutions to everything around us. As the generation and usage of data is increasing exponentially nowadays, we do need efficient techniques to store and transform data. Now, there are two methods for data compression, which include first, lossy compression and second, lossless compression. Now, for lossy compression, as the name suggests, it loses data. It gets rid of it to reduce the size of the data. Now, lossy compression is performed quickly and it reduces the file size significantly, but it cannot return the same data on its decompression, which is the main point. Now, for lossless compression, it on the other hand does not remove any data. It transforms the data to reduce the file size. Lossless compression transforms unnoticeable data by using some formula or logic. So from this, we can clearly understand that lossless compression is a very important tool and it is much better than lossy compression. So these are some common lossless techniques, and from this, I'm only gonna study 4 of them: that run length encoding, Burrows-Wheeler transform, move-to-front transform, and Huffman coding. Starting from run length encoding. Consider a screen containing plain black text on a solid white background. There will be many long runs of white pixels in the blank space and many short runs of black pixels within the text. A hypothetical scan line with B representing a black pixel and W representing white might read as follows. This one. After performing RLE, we'll get the compressed data as following: 7W, 5B, 3W, 1B, 6W, 4B, which is a compressed version of the input string. Next comes Burrows-Wheeler transform. Now, to understand this technique, we take the example hash banana hash. Now, there are 3 main steps in Burrows-Wheeler transform. Step 1, it forms all the cyclic rotations of the given text. So, for this given text, here are all the possible cyclic rotations of the given string. Now step 2, we sort all the strings given here lexicographically now. So when these strings are sorted lexicographically, we get this whole bunch. Here comes the step 3. The last column of the lexicographical strings is taken as our BWT. So the BWT of hash banana hash is equal to A hash NNB hash A. And we have to store the index as well, which is in this case 0, 1, 2, 3, 4, 5. 5 is the index and we have to store that index as well. Now is the next algorithm, which is move to front transform. In move to front transform, step 1, the primary idea behind MTF is to maintain an ordered list of legal symbols A to Z. Step 2 is reading one character at a time from the input string. Step 3, print out the position at which that character appears in the list. Step 4, move that character to the front of the list and repeat the process until indexes for all input characters are obtained. So here is a final sequence for banana, BANANAAA, and this is 1 1 13 1 1 1 0 0. Now comes Huffman coding. Now, in Huffman coding, the idea is to assign variable length codes to input characters. Lengths of the assigned codes are based on the frequencies of corresponding characters. Now, The main idea behind Huffman coding is that we assign least binary code to the most frequent character. Now, the variable code lengths assigned to the input characters are prefix codes. Means the codes are assigned in such a way that the code assigned to one character is not a prefix of code assigned to any other character. This is how Huffman coding makes sure that there is no ambiguity when decoding the generated string. There are mainly two major parts in Huffman coding: build a Huffman tree from input characters, traverse the Huffman tree, and assign codes to characters. Now, how we create this Huffman tree? So, for example, let us take 6 characters A, B, C, D, E. Build a minimum heap that contains 6 nodes where each node represents root of a tree with single node. In step 2, extract 2 minimum frequency nodes from minimum heap, add a new internal node with frequency. 5 plus 9 is 14. Now, minimum heap contains 5 nodes where 4 nodes are roots of trees with single element each and 1 heap node is root of tree with 3 elements. Now in the step 3, we do extract 2 minimum frequency nodes from heap. Add a new internal node with frequency 12 and 13, which is 25. Now heap contains 4 nodes. In the step 4, extract 2 minimum frequency node. Add a new internal node with frequency 14 and 16, which gives 30. Now heap contains 3 nodes. In the step 5, we extract 2 minimum frequency nodes, add a new internal node with frequency 25, 30, which is 55. Now heap contains just 2 nodes. In the step 6, extract 2 minimum frequency nodes, add a new internal node with frequency 45 plus 55, which is 100. Now heap contains only 1 node, and thus the algorithm will stop here. So you can see from this Huffman table here, Huffman tree here, that here is our whole Huffman tree, and we took A, B, C, D, E, and this is how we traversed. Now after the whole Huffman tree is made, we assign the left string 0 and the right string as 1, and just do it. So 0, 1, 0, 1, 0, 1, 0, 1. Now, how do we write the code? So this is how we write the code. Now if I want to write the code for A, then I must start from the root, which is here 100, and then go all the way till A, which is 1, 1, 0, 0. So the code for A here is 1, 1, 0, 0. Now A was not so much occurring, but if we see the element which was occurring the maximum, which was F, which is 45 times occurring. So if we see its Huffman code, it's just 0. How much space is saved here? So in this way, Huffman code tries to simplify everything for us.
So this was all from the PPT, and now we'll see how the application works.
Now let us see the working of our application. So now this is a test file. Now first of all, we should place all the 4 main files in the same folder and our test file as well. So this is our test file, and here in the properties we can see that the test file is of 50 KBs. Okay. So now we run it in the terminal, and here we write Python space data tab, enter, and so we get the window where there are 2 buttons, to compress and to extract. Now for compression, we must select a file of .txt. So here is our test file.txt. We select it and we press open. So the compression has started. As we can see, the main.out has been created here. It will take some while. So the compression has been done, and you can see here the compressed file size is 8812 bytes, means 8.8 KBs, and we selected our original file was 50 KBs. The compression ratio is itself 82.37%. It is a very huge ratio. So here's our hi.mkg file. The compressed file will be of .mkg extension, and see the size of it is 8.8 KBs. Okay, so now we will extract the file and see if the same decompression happens as well. So here we selected the hi.mkg file and open it. Here even it may take some while. Oh, file has been extracted and the extracted file size is same as our original file size in the previous case. It is 50 kbs. So here it is a lossless compression and we have been successful to achieve it. Fifty kbs. This was our original file.
So this was all from my side. Thank you very much.